All right, I think we're all set up. All right, so there is this aspect of magnetism, and this is what I want to get across to you. We don't need to explain a lot about what magnetism is, and you'll read that in the book. Um, but the one thing about magnetic fields is that they don't exist all the time. Okay, and that's very different from the electric and the gravitational field, because with the electric and gravitational field, they just are there all the time as long as you have the property that causes them. So if you have mass, then you exhibit a gravitational field, and that field will interact with the other gravitational fields around you. If you have electric charge, then you will exhibit a electric field, and that electric field will interact with other electric fields around you. But the magnetic field only exists if the charged particles move. So that's very different. It's almost like the magnetic field is almost like the wake of the electric field. And if you don't know what a wake is, what I'm referring to is not like in a funeral. What I'm referring to is when you're in the water in a boat and you look behind the boat and you see that kind of V-shaped where the water has been pushed out, and it sort of forms that V shape that just gets wider as you get farther away from the boat, and that's called the wake of the boat. And the magnetic field is a lot like the wake of the electric field. It's like this thing that appears when charged particles move, and when they stop moving, it disappears. It ceases to exist. So we have these two different kinds of magnetism, permanent magnetism and electromagnetism. We will focus more on electromagnetism, but we will definitely look at the permanent magnets. Permanent magnets are quite complex. It's a very challenging thing. It's not as simple as the electric and gravitational field. But one of the problems that we're going to run into with the magnetic field is that we must be able to represent three-dimensional space on a flat piece of paper. So for that purposes, I'm going to show you the symbols for directions. And some of them you know, but some of these will be new to you, and I need you to start getting used to them right now. What I am telling you is not specific to magnetic fields, it's simply specific to directions. These directions could represent anything: magnetic field, force, velocity, acceleration, momentum. It can represent anything. But it's really important to be able to show three-dimensional space. So I can show two-dimensional, right? Left and right, up and down this way, but I can't show out of the page. How would I show something that was coming out of the page or maybe going into the page? That's where we're going to run into the difficulty. So let's start with the basic arrows. I know this might seem stupid that I'm drawing arrows to show you what left and right means, but I just want to have it all together. Okay, so now the two into the page and out of the page. Now, the way I drew my arrows is, like this is the way we draw vector arrows. I don't draw feathers on the back of the arrow, because I'm not trying to draw like an actual, like literal, an arrow, like from a bow and arrow. But in reality, the arrows from a bow and arrow, they do actually have feathers or some kind of thing to help guide it, right, to keep it lined up in the right direction. And so if you imagine that we were looking directly into the arrow, so let's imagine that we were over here and we were looking straight at the point of that arrow, what would it look like to us? Well, I would argue that it would look like this. That what you would see is the tip of the arrow, and then you would see the rest of the arrow as it moves away from you, right? As the arrow moves away, you see the rest of the arrow is out here, and then you can't see the shaft of the arrow because it's behind the point of the tip right there. So a circle with a dot represents an arrow. So I'm going to try and point this right at the camera. See how close I can get. Just like that, right? The arrow's pointing directly at you. What do you see? You see a circular thing with a point on the tip, right? What would it look like if it was reversed? What if this guy was facing this way? Well, then you would be looking at the feathers. So the way we represent that is a circle with an X. So I can represent to the right on the page, to the left, up the page, down the page, or out of the page, or into the page. Out of the page like this, into the page pointing like this. And that's going to allow us to represent three-dimensional space. Okay? Any questions about that so far? That feels like that's not a lot of new stuff, but those two symbols on the end, those will be new, and you need to get really familiar with them. There needs to be this just instinct that you just look at it and you just know that's out of the page, that's into the page. And it will really help if you visualize what it is that you're looking at. You're either looking at the tip of the arrow or you're looking at the feathers, and that's what's being represented by these. So it's very logical. It does make sense. It's the best we can do. That's the best we can do on a flat piece of paper to represent three-dimensional space. All right, so I'm going to show you both of the right-hand rules. Believe me, you're not going to get it right now. I pretty much guarantee you. I've watched a lot of students try to learn this, and I don't know what the deal is. I really don't know what the deal is, why it's so difficult to get, but it does seem to take a long time for people to get. So let's look at the right hand rule. Now, first of all, we have the right hand rule because we have right hands. So that's very convenient. And I bet most of you take your right hand everywhere with you that you go. So if you were on, like, say, for example, an IB exam and a question involved the right hand rule, you could use your actual right hand to guide you to think about what is the direction of either the magnetic field or the force or whatever the property they're looking for. The right hand rule is going to help you with that. Now, there is a left hand rule, and we will talk about the left hand rule, but I'm not going to talk about it today. We're going to look at just purely where the right-hand rule shows up in magnetism, and there are two places that we're going to look at. So the first one is the magnetic field around a wire. This is not the first law. There's no such thing as like first or second law this way. It doesn't really matter. There's no order. Now I'm actually going to say one more thing around a current carrying wire. Okay, wires don't have magnetic fields, but when they have current, they do. As soon as you put current into that wire, you get a magnetic field. And I will show it to you. I have a bunch of stuff at work that I'm going to go pick up next week, the beginning of the week, and I'll do a bunch of demonstrations for you to show you that wires do produce a magnetic field. It's very obvious. Like, there's no way you won't notice it. If you had a very small compass and you had a lamp, you might even be able to get the lamp to show you that magnetic field, but by putting by putting a compass near the cable, you might notice it'll deflect a little bit when you turn the lamp on and off. But it's difficult to visualize, right? It's like a very hard thing to visualize. So I'm going to give you the parts of your hand. So the two right-hand rules work a little bit differently. So the first right-hand rule has two parts, your thumb and your fingers. But your fingers are going to curl like this. So it's almost as though you're holding a wire in your hand like this, and then you're going to take your thumb and point it in the direction that the current is moving. And remember, current is based on the direction of the positives, right? That's a little bit of a weird, that's a little bit of a strange thing that we all have to kind of get used to. We base everything on the direction the positives are moving, even though that's not actually what's happening. So I will take my thumb and run it along the wire in the direction of the current, and then I will wrap my fingers around. And that is the shape of the magnetic field around a wire. It forms loops, closed loops, that wrap all the way around the wire and return back to the point where they started. So let me give you a description of the parts of your hand, and then we'll practice it. So first of all is your thumb. This is the direction of the current. And I'm going to put this in here just to make sure you don't forget this, the positive. Even though in reality it's actually the negatives moving the other way, it doesn't make any difference. Everything still works out exactly the same. Okay, so the thumb gives me the direction of the current, and my fingers, and I'm going to add something to this. It's not just my fingers. My fingers must curl. This is really important. The two rules work in slightly different ways. My fingers are the direction, and if this is not obvious, let me just actually say it. The right-hand rule only tells you the direction. It doesn't tell you anything about the magnitude of the force, or it won't tell you anything about the strength of it, but it will tell you what the direction. All right, so your thumb is the direction of the current, and your fingers are the direction of the magnetic field. All right, so let me give you some examples, and then I think it will become more clear, but it will just take a little bit of practice for you guys to get this down. So let's say, for example, that I have a wire, okay, and I'm looking directly into the end of the wire, right? So this is like the circular end of the wire, and I know that there is some current. So what this drawing is telling me is that I have a wire, it's oriented like this, it goes directly into the page, and the current is traveling this way, into the page. The current is traveling into the page. So now the question is, what's the direction of the magnetic field? So I'm going to try and do this on the video. It's going to be a little difficult because it's like I kind of have to turn my hand to get things to line up. But what I want is I want my thumb to point in the direction of the magnetic field, and then my fingers are going to curl in the direction of the magnetic field. So in this case, my fingers are curling in the clockwise direction. They are curling like this. And the symbol for magnetic field is B. Now you can imagine that if we did the opposite, what if we had a wire and that wire had current coming out of the page? Well, then I would hold my thumb like this, pointing out of the page, and I would wrap my fingers around the wire to see the direction of the current, and I would see that the direction of the current was in the counterclockwise direction. So for a wire carrying current out of the page, the magnetic field points like this. Exactly the opposite. Exactly what you would expect the magnetic field to do. Of course, it's going to be reversed if we look at it from the other side. Okay, so that was easy to do. Now, there's actually concentric rings. So I could draw more and more and more rings. What essentially you would see is that as we get farther away from that wire, that magnetic field gets weaker and weaker and weaker. Right? It follows a similar rule to what electric field and gravitational field. It gets weaker when you get farther away. So I could just draw concentric rings getting bigger and bigger and bigger around this guy, and those would represent the magnetic field lines. When I turn the current off, they disappear. All the field lines disappear, and the entire magnetic field disappears, and there's no magnetic force anymore. Okay? What about the other pictures, right? So we did into and out of the page, but what if we had one of these? Then what would you do to show the magnetic field? That's a little bit tricky. So let's try this one first. All right, so if I say that that's I, then here's a really helpful thing. Use your pen, because one thing about your pen is you can pull it off the page. So right now, what I want to do is put my thumb along the direction of the current. Oh, yes, because I'm lazy and sloppy. Yeah, B is a direction, and this all we're talking about is direction. So yes, I do think that it would be wise to put that vector symbol. I don't think you're going to be deducted if you don't put it, but we're only talking about the direction, so it does feel like you probably should have that vector symbol on there. So the trick with this one, though, is that if I put my thumb along the wire, then I try to imagine wrapping, but that's hard to do. My fingers won't go through the paper. I can't get under it. But if I put a pencil there and I lift the pencil up, I can run my finger along the wire in the right direction, and now I can imagine that magnetic field wrapping around the wire. So look what's going to happen. On the left side of the wire, look at the direction of my fingers. They point out of the page. But what if I look over on the other side? They point into the page. So to the right of the wire, the magnetic field lines are diving into the page, and to the left of the wire, the magnetic field lines are exiting or emerging through the page and coming out. I mean literally. They're literally coming right through the page. That piece of paper is not going to stop the magnetic field from coming through. So I'm going to draw just one circle on this side and one circle on this side. And remember, on this side we said coming out of the page, and on this side we said going into the page. And the reason why I drew the two of these like this is because that's one loop, right? Imagine the loop. It comes out of the page, it goes up over the wire, and then dives back down here. Now the other part's going to be really hard to see because it's under the paper, but under the paper, imagine if I had another pen here, under the paper the field goes down underneath and then re-emerges back on the other side, coming out on the left hand side. So I feel like if you're going to try and draw the magnetic field around a wire, you should draw, in this situation, you should draw two circles, one to represent where the field exits the paper and one to represent where it goes into the paper. And that's enough because there's really nothing else you can do, right? All the other directions are hovering above the paper or they're hovering below the paper. So we don't need to draw that stuff. Okay, and it wouldn't make a difference. Let's say, for example, I did it this way. We'll just do one more because I don't think this is the most challenging concept. So again, same thing. Here's one thing I would really suggest. Don't sit there turning your hand into some weird until you hurt yourself. Okay, please do not hurt yourself. Notice the piece of paper moves, right? We're not writing on a rock that's attached to the ground. Like you can turn the piece of paper. Turn the paper so that you can conveniently line your thumb up with the picture. Okay, this is how it goes. You write the picture on your paper, and then you use it as a guide to line your hand up correctly. So here's my thumb pointing in the direction of the current, and I see that my finger on the bottom side of the wire goes in, and if I wrap my fingers all the way around, I can see that above the wire, that I can see my fingers are pointing out of the page. So now I'm going to go ahead and draw. I'm just going to remind myself, oops, sorry, out of the page above, into the page below. And try to make them symmetric because it would be symmetric. These two would be equal distance from each other because they're part of the same loop. Okay, any questions about that before we move on? Is there any errors? You see anything that I might have missed? Because it's probably did. Part of the thing with the wires is that they produce a nice simple field. It's just these nice simple circles. They're very easy to draw. They're concentric circles. That makes it much easier. Now we will look at the magnetic field in other situations where it's not as simple as that. So we will talk about the magnetic field a little bit more deeply when we get into on Monday. But let's go on to the second right-hand rule. And when I say the second right-hand rule, I don't mean like literally the second right-hand rule. They're not in order. There's no order to these. So this is one of the right-hand rules. It's the one that tells you the magnetic field around a wire. And now what we want to look at is what happens if you put a wire. So number 2 is all right, so this might not be obvious to you, but let's just think through the logic of it. If you put current in a wire, the wire becomes a magnet. Okay, simple as that. If you put current in an electrical wire, that wire becomes a magnet. It will behave just like a magnet. It will exert a magnetic field, the compass will be affected by it, it will be attracted or repelled from other magnets, depending on the orientation of the field from that other magnet. So what would happen if you put current in a wire and then you took that wire and you put it into a magnetic field? Well, what would happen is there would be magnetic force. Now, when you put a wire into a magnetic field, there's not going to be any force, but as soon as you put current in it, the current makes the wire become a magnet. And now that magnet is going to push against the other magnetic field, right? So when there's no current, the wire just sits there, nothing's happening. In the magnetic field is irrelevant. But as soon as you put current in there, the wire will become a magnet, and because it's a magnet, it will now interact with the other magnet, and you may see force. Now, it's not guaranteed that you'll see force. There's ways where you might not see the force, but essentially a wire, because it is a magnet, that's why when we put that magnet or that wire in a magnetic field and we put current in it, it acts as though something's pushing on it. It literally, you might even see the wire bend. The wire might do this as you put current in it. It might actually bend because of the magnetic force, not the electric force, the magnetic force that is being applied to it. This rule is a little bit more complicated. It involves using your entire, not your entire hand, but more of your hand than the other rule does. So let me give you the parts. This will be very easy for the first one. This is the direction of the current. Okay, your fingers. Now here's something that's going to be a little subtle. It's not subtle, actually. Let me say it's not subtle. This is what the problem is, that oftentimes it's treated by students as being like a very subtle thing, but it's very profoundly different. When I drew the diagrams before, my fingers were representing the magnetic field of the wire. Okay, I used my fingers to represent what the shape of the magnetic field would look like around the wires. Now, I am still going to have my fingers represent the magnetic field. But the difference is the magnetic field is not coming from the wire. It's coming from some other thing. Maybe I have two bar magnets. I put one magnet here and I put one magnet here, and then I get a strong magnetic field in the middle. And then I put a wire in there. Okay, and I will see force act on that wire as a result. Maybe I have an electromagnet on this side, and it's producing a magnetic field over here. I don't know where the magnetic field is coming from. But the magnetic field that your fingers represent does not come from the wire. Because again, just let me remind you this, when we talked about the third law, we talked about how the third law allows you to propel yourself. But it only allows you to do that by pushing on other things. You can't push on yourself and propel yourself. I just assure you, it will not work. You can push on yourself as hard as you want. You might hurt yourself. You might leave bruises or even break a bone, but you're never going to make yourself move by pushing yourself. Every time you move, it's because you pushed against something else. Maybe it was the seat, the ground, the wall, the table, whatever. So similar thing is going to happen here when we talk about the force that is exerted. Oh my God, you gotta be kidding me.